domain and range. So really quickly, before we totally jump into domain and range and that graph and the example that you guys have that you were looking at, can I ask you a quick question? Yeah. What were the domain problems? Without looking back in your notes. I need to zoom out. You guys can't see it, can you? No. Oh, that's okay. We'll just do this. I need to write a lot smaller, don't I? Okay. What were the domain problems? Roots? Is that the only one? Okay, so we need to worry about denominators. So guys like this, right? They have a problem. And then you said roots? Okay. So guys like this. And then logarithms. Can I just use an ln? Because he's like one of the most basic ones. Is that all right? Yeah. So ln of, wait a minute. I'm putting weird stuff like f of x over g of x and square root of f of x and ln of f of x. What was different when we did it in section 1.4, which you guys helped me figure out yesterday? Yeah, there weren't f of x's and g of x's, there were u's, right? Yeah. There weren't f of x's and g of x's, there were u's. So I am using function notation. Now that we've done function, I'm using function notation to replace the u. So if I was thinking about domain, for instance, for this whole, let me do a different color, f of x over g of x1. Instead of doing, oh, that's horribly light. Well, it is, right? It's like a pink. It's not even red. We should sue. Okay, don't sue. That's bad. Okay. You guys might be remembering, if you remember at all, like, oh, we would use a u to be greater than or not equal to, or greater than or equal to. Which one's which? But we're not going to use a u this time. What are we going to use now? Okay, so f of x. What's true with denominators? Wait, denominators. Who's the denominator? Oh, okay. So what can't be true of denominators? Okay, but hold on. What's the domain trying to find again? X values. So we would have to take this expression, and wouldn't we have to solve for x to fill in our domain? Yes. Okay, cool. And that's usually going to be with factoring whenever we're dealing with zeros, right? Okay. What are we going to do for the second one, for radicals? What do we have to think about for domain? Okay, well, if you want to remember what's going on, you can go back in your notes to section 1.4 because there was a place in section 1.4 where we talked about domain problems. So I've been saying it, but I haven't actually shown it to you. So if you're totally lost, go back, section 1.4, find where we talked about domain problems. There were u's, but we're not talking about u's anymore. We're talking about function notation. So if you have a denominator, you're trying to answer domain. In order to answer domain, you have to think about the denominator can't be 0. But if you have a radical to get to the domain, you have to think about how the argument has to be greater than or equal to 0. AKA, you can't have negatives under an even root, right? So it has to stay positive, and that's a greater than or equal to 0. And then for ln's, what was true about ln's? I know we haven't done logarithms, but do you remember?
Domain has to be greater than 0.
Domain is going to be found by setting the argument greater than 0. I just wanted you guys to connect in your notes. You don't necessarily have to write this down. I just wanted you guys to connect in your notes the idea that, okay, this should be able to zoom out. This is weird. Oh, there we go. I knew something was weird. I want you guys to connect the idea that in section 1.4, when I said u, it was just a simplified way of explaining what was going on. When I say u, I kind of mean function. So now that we've talked about function notation, when I said, hey, denominators can't be 0, so whatever function is down there can't be 0. Solve for the zeros, that will tell us our domain. Square roots, when I said u has to be greater than or equal to 0, what I meant was whatever function has to be greater than or equal to 0, solve for the domain. And then when I talked about logarithms, the exact same idea. Because when I use u's, you were like, okay, fine, whatever, u. But now if I put function notation in, maybe it makes more sense as to why we have to solve for x to get the domain. And to be honest, this can be a really hard thing if you have like a polynomial and you have to factor. Factoring can get really hard. We're going to have to review some stuff today and see how good you guys are at factoring when there isn't a leading coefficient of 1. And then logarithms can be kind of messy as well. Inequalities just get kind of gross sometimes with like number lines and intersections and unions and But I just wanted us to realize with the domain problems, I showed you in section 1.4, when I say U, I mean function. Does that kind of make sense?
Yeah.
Okay. So if you want, you can go back to your notes. And you can totally go to these domain problems and say, U, solve U for X. Oh, she meant every time like f of X or a g of X or an f of X, which is why you need to get X by itself to solve. The domain problems is just an important thing. I'm going to keep on bringing your attention back to it, and especially today, because what's the question that your notes started off answering today? Domain and range. Now pause real quick. Let's go back to intervals. Before we start using intervals all day today, let's review that we know what they mean. Remember that an interval shows you how low to how high. How low to how high. Maybe for x's, maybe for y's, maybe just for like an interval of numbers. But it shows you how low to how high, separated by a comma, and limited or marked by either a parenthesis or a bracket. When do you have a parenthesis? Okay, you can just read that not equal to, but what does that mean? What kinds of inequalities will have a parenthesis? Greater than, that's it. Or just less than, that's it. Or anytime you have an infinity or negative infinity. Why? Why is that automatically going to be a parenthesis? You can't be at infinity. You can only get closer and closer and closer. So anytime you have an infinity, it's an automatic parenthesis. It's an automatic parenthesis. But if you have a constant, you have to think about, okay, is it equal to or is it not equal to? Now guys, if we were to do number line graphs of these ones, just real quick, because that might come up every now and then, number line graphs. You would have -2 as a placeholder, and you would have 5 as a placeholder, right? And the number line would keep going, and would keep going. What kind of circle would you put at -2? Empty or filled? Empty. So you're keeping the circle open, right? And then what kind of point would you put at 5? Filled, because it's or equal to. Do you guys remember these number line graphs from a long time ago? Okay. Here's another way of remembering parentheses and brackets. Ready? Parentheses keep it open, limited by, but keep it open, whereas brackets close it off, right? Silly way of remembering it. But parentheses keep it open, whereas brackets close it off as far as equal to and not equal to. How would you do a number line graph for this guy? X greater than or equal to 3. Filled dot at 3 and the arrow is going what direction? Greater than or equal to. Do you see why 3 was on the left and positive infinity is on the right? Aiden, I see you. Give me 1 sec. How would you graph x less than 1? Empty circle? And then arrow pointed to the Do you see why 1 is the highest it goes and negative infinity is the lowest? So every time you're doing an interval, you're asking how low to how high. Not so much with graphs, we're going to get that in a second, but literally the lower value to the higher value. And so the lowest value on this one was -2, the highest value was 5. We kept it open and we closed it off. This one, the lowest value is 3, closing it off, and then infinity is how high it could go. And this one, 1 is keeping it open, but it's on the upper end, and negative infinity is on the lower end. Aiden, what's up, buddy?
You answered my question.
Cool. I was hoping. Okay. Intervals. Any question on in general? Intervals. Parentheses. Brackets. What's on the left? What's on the right? Where to put the comma? What's the one thing you have to look out for with intervals? I'll show you over there. Ready? Domain and range. That didn't work very well. Go forward. There we go. Domain and range. You guys remember this from the other day with my little nifty illustration, yeah? That I made real fast? Okay, it's your faces. Don't worry. There we go. Okay. So what questions do domain and range answer? Domain answers how far left to how far right. And then range answers how low to how high, or how down to how up. True? So when we're doing intervals, here's what I need you guys to realize. When we do x with this little e, or y with this little e, it literally means this little e, if you want to write it down, is an element of. It's basically saying like x can be any value inside this given interval, or inside this given set. But I'm going to show just with parentheses, because parentheses are the most confusing with intervals. Can anybody tell me why? If there were just parentheses, why is that the most confusing interval notation? Exactly. People are going to think it's an ordered pair. Is it an ordered pair? No, an ordered pair is how many locations? If I gave you like 2, 1 and told you to graph the point, how many locations is there? 1. You can even be super snazzy and go back to geometry and talk about how a point is dimensionless and isn't really there because it doesn't take up any space. That's mind-boggling. But a point is one location, one theoretical location. But what's this talking about? An entire length of values from A all the way to B. It has a totally different meaning. So we're just going to put down here really quickly, okay, with A to B intervals. Watch out. Here's a struggle. Without context, you won't know. Without context, you won't know. You guys know there's a verse in the Old Testament, actually kind of a whole passage. It talks about disobedient children and how they should be stoned. The law was really rough with the Israelites in the Old Testament. Why am I talking about that? Some people use that, or could use that, in or outside of its proper context to be like, oh, my kid disobeyed. Right? Now, should they use that? No, because in the big picture of Scripture, that's not where we're living. We're not living with God trying to be like, I am a gracious God compared to other gods, but you need to see me as holy and set apart and how we cannot go after. Okay, there was like a meaning, there was a context to the Old Testament, and Jesus is throughout the entire Bible. I'm not a Bible teacher, I'm going to stop. But things taken out of context can be used very dangerously, right? Or even wrong. True? Why am I trying to warn you about interval notation? If you don't look at the context, you're like, it's a point! And you're totally wrong. Because instead, it can mean a whole range of numbers. Okay, I'm going to get in danger, or this is a danger zone. Do you guys know how some math words have like English meanings? If you go to the gun range, is it talking about Y values? No.
I've never been to a gun range.
Okay. But you know what it is?
No.
No? Never mind. How about if I was to say like, hey, what's the range of your scores on the last test? I'm not talking about Y values. Well, maybe I am if you define the function to be the student's test scores and the inputs are the student's names. Anyway, I guess you could make it weird and mathy. But usually if you use range in English, well, gun range is totally different. But if you use like a range of numbers, or range of heights, or range of whatever, it just means beginning, end, a list. I don't know. It's like this whole interval. So there's a struggle. I'm going to try to use the word interval to talk about the English word range, because in math, range means Y values. And if you don't know what I'm talking about, fine. Range, Y values, that's it. If I use it out of context, let me know. Okay, so intervals. From A to B, an interval of numbers. We have a graph. Let me zoom in. Some of you guys were able to see the details. Some of you, it was too small. You'll learn. My computer hates me sometimes. I don't know why. Oh, it's because it's frozen. Okay. Here we go. I'm asking for the domain. We're answering the question, how left to how right, and we're looking for an interval. So, I'm going to go ahead and start off with x is an element of. You guys know how to write that?
X with a little e.
X with a little e. Got it. I'm going to fill in a how far left spot to a how far right spot. So right now, I'm just showing the spots to fill in. And I'm not going to give brackets or parentheses because, frankly, I don't know until I look. Yeah? Okay. How far left does this graph go?
-1.
And you have to be careful because I'm not looking at the height, I'm looking at the x, right? So how far left? -1. How far right?
2.
2. But it's not at 2, so I should use like, wait a minute. 2's not even 5. Got you. Okay, so it's supposed to be 5. Because I'm seeing how right it goes, which is 5. But wait, it's not at 5, so I should choose like 4, right?
No.
No, because we're at 4.5 and 4.9 and 4.9. Okay. So I have to say 5 is my boundary, but how do I say not including 5? I keep it open, but on the other side, I'm closing it up. Does that make sense?
Yes.
How left to how right with intervals, it's super applicable because I literally am putting how left to how right in the domain interval notation. Now, range. Let's pop down to letter C. Range. What am I answering now?
How high to how low?
How high to how low. And I'm not doing x as an element of, but y is an element of. How low does it go?
3 and 3. 3 and -3.
How low does it go?
-3.
Start with the lower value, -3. How high does it go?
3.
Am I keeping any of them open? Am I closing all of them off? Am I doing half and half? Why am I closing all of them off? They're both solid, exactly. Now, a few people might be like, but wait. And you're smart if you're thinking this. But 2 cannot be included, so somehow I have to say from here to here, but not 2. And I would say, okay, the 2's not included here. The question is, 2 hit somewhere along the line?
Yeah.
So I'm going to include the 2 because it will be one of the ranges with one of the points. Can I ask you a quick question, though? What if, I just lost the whole thing. What if they hadn't cut off the graph? Just a quick what if.
Then
What if? You can even do a different color if you want because we're kind of changing the scenario. What if this kept going through the hole and this kept going through the hole?
Yeah, it'd be infinite.
Yeah, and you're describing it well, but your intervals are off. You're right, it's infinite. You're right, it's all real numbers. But what was my interval?
Well, no.
Infinity.
Yeah.
To infinity.
Because how left would be -infinity, how right would be,
And then range would be the same.
except y is an element of, right?
Yeah.
Because it'd be forever loaded for us.
The E is showing you that it's an interval from here to here instead of just a point.
Daniel, hang in there, bud. Are you questions like back? Did these ones make sense? Did these ones make sense?
No, that's fine.
It's the interval notation that's messing you up. I think you're still thinking of a point, like an ordered pair, like graphing a point. Like these are points. Go -1, +1, or go 2 and -5, or -3. These are points, but when you have this little e, we're saying, hey, when does it start and when does it stop? So if I take away the green lines, this graph starts at a bottom height of -3 and it stops at a top height of 3. The start and stop of my y's or of my heights. And the start stop of my x's was -1 to 5. So this comma in math or even in computer programming doesn't always mean an ordered pair. The comma can be like separating a list of numbers. The comma can be representative of the word to, which is what it means in this one, from -3 to 3. So it's talking about a whole interval. Beginning, ending, beginning, ending. Think beginning, ending. Let's see if that can make a little more sense as we go through. Oh, that's the eraser. But there was another question. No, I thought someone raised their hand. Just kidding. I'm making up stuff. It happens. All right. Zeros. I'm going to give you 2 pages because there really isn't many notes on this. This one, you get to take a quick break from interval notation. So those of you that are like, ugh, hold on. No interval notation on these 2 pages. We come back to it in the next type of problem. Because zeros are just locations. There's a 0 at this point. There's a 0 at that point. We're not talking about intervals. Unless the graph hits the 0 for a long, long, long time. But Otherwise, zeros are just singular locations. But that's weird. Didn't we already talk about x-intercepts, like, I don't know, back in section 1.2 or something?
Yes.
1.3, 1.4. We already talked about intercepts and symmetry, so why are we back here?
Because when you find the intercept, there's always a 0 either the x or the y.
Yeah. What we used to call x-intercepts, and we're not going to stop calling them that, but what we were originally calling x-intercepts can also be called zeros of a function, because as soon as we talked about f of x, function values, y values, we can say the function has zeros. It's a new way of, a new terminology, a new vocab in a sense. Function values, y values, f of x equals. It's just new notation now that we've talked about f of x. So x-intercepts, that's review, but zeros of a function, that's what's new. So when they say find the zeros, what zeros? X or y intercepts? No, you don't need to ask that question. If they're saying find the zeros, they mean the function's zeros. And the function's zeros is f of x zeros, which only refers to x-intercepts. So it's kind of just figuring out what they're saying when they're saying find the zeros. The function zeros, the f of x is zeros. AKA, set the function equal to 0. However, why do some of you not like this as much as the ones that we saw the other day when we were doing x-intercepts? What do we need to do? Factor. Or quadratic formula, or complete the square. But most of you really hope that factoring works, but what makes this messier, and so we have to review just for a second.
Or 3 in front of the extra one.
Yeah, the leading coefficient of 3, yeah. So if the leading coefficient is 3, some people would call it a modified x method. I think that's what Mr. Che called it. Some people have a box that they do. Some people guess and check and just put parentheses and fill in answers. That's how I learned. But for those of you that are modified x people, can we make sure you know how to do the modified x? Whenever you have a value in front, what do you have to put in the top of your modified x? A times z. Yeah, the product A times z. Yeah. So what's 3 times 10?
Negative
30.
Ooh, times negative 10. Good catch. What goes in the middle? The coefficient, which is 1. And then we're looking for 2 that multiply to be negative 30 and add to be 1. But pause. Technically, that multiply to be negative 30x squared and 1x, right? Technically. We just shortcut it and only write the numbers. Why am I saying that? Well, first of all, what are the coefficients?
6 and negative 5.
6 and negative 5. But do you guys realize those are technically x terms? For my cool people that are box people, you would have looked at this as a 3x squared, and you would have looked at this as a negative 10, and then you would have gotten the, oh, hey, cool, that's a 6x and that's a negative 5x. That's how I could have gotten if you'd done this work off to the side. There are some people that are box people just hanging out. And then you could have factored out what was in common, and actually gotten to your common factors that way. Actually, some people might actually make that a 30. Depends on how you do the box method. Most of you have done the modified x. I know, I'm coming back. But why do I tell you this? How do you get to the final factors? Group. When there's a leading coefficient, you don't go straight to x minus 5 and x plus 6, because technically that's not true. You have to get the meaning of what the 6 and the negative 5 are. And then you have to ask yourself, what's in common? What's in common between the 3x squared and the 6x? 3x. And what's left is an x plus 2, right? What's in common between the negative 5x and the negative 10? Negative 5. Careful. What's left? Plus 2. Good. X plus 2. Now, what's in common? There's an x plus 2 in both. So that comes out. And what's left when you pull out the x plus 2? Now there are other ways of doing factoring. So if you're like, yeah, Mr. Che did that modified x thing and I never got it, can you come see me at grab out a whiteboard and we find a way that works for you? There are lots of ways to do it. Or if you're like, I came from somewhere else and we did something else, cool. Come show me because you probably need to review your way of factoring. Let's make sure that you know how to do it and do it well and do it right every time and we'll go from there. There's a few different ways of thinking about it. And if you guys want to be really tripped out, you actually could do something crazy where you do this little division thing. And with this little division trick, actually some people just draw a line through it. You can get straight to the answer without grouping, but maybe that's a discussion for another day. Well, do you guys want to see? Yeah. If you take your modified x, but if you divide, you're welcome so much. If you divide by negative 30, and if you reduce, what would you end up with? And if you reduce that one, what would you end up with? Wait. You can tell I haven't tutored this way in a while. It's a cool one once you do it right. It's not negative 30. Sorry, what was your leading coefficient?
3.
Yeah. Now you reduce. You end up with a 2, and you reduce, you end up with a negative 5/3. You can actually kind of sneak ahead to the final answer. But you have to know how to read it, and it's really a trick. It's not like an actual mathematical process like grouping is. So there are tricks to kind of get to the final without doing grouping. But for right now, I know what you guys saw in Algebra 2 with Mr. Che, which is the majority of us, and that's exactly where we've gotten right now with the x plus 2 and the 3x minus 5. But we're not done yet, because what were our directions?
Find the zeros.
Find the zeros. So, the whole reason that we factored is because back here, if you try to figure out what adds to be 0 perfectly with this pattern, it's going to take you forever, or maybe you'll never get there. But if you get down here to the factors, how do I multiply to get 0? Well, either that one's 0 or that one's 0. One of them has to be 0 to get that. So we say, cool. Let's take this first one, set him equal to 0. Let's take the second one, set him equal to 0. And most of you kind of do this in your head and you don't actually show the work, which is okay as long as you get it right every time. Some of you, I think in Algebra 1, I did little equals 0, and we solved off to the side. But either way, we need to take each factor, set each one equal to 0, and there we go. Which we kind of reviewed once again when we did x-intercepts, but leading coefficient just gets a little bit messier, so we have to be careful. You have to be careful. Now, if I was to give you a graph of this dude, this parabola who's ended up shifted and stretched and all sorts of jazz, let's get all that jazz, all sorts of stuff, either way, I put it together. Do you guys see how we were technically right with the negative 2 and the 5/3? So if they ask for find the zeros and you have a graph, it's easy, just look for the x-intercepts. Or if they want you to check graphically that you're right, you can just sketch the graph, get a nice pretty window, and go find the zeros. And if you guys want, there's technically a 0 function in your calculator if you want to find it out early in the second trace menu. It's called zeros. Literally, it's how you find the x-intercepts. Even your calculator knows this terminology. The zeros are the x-intercepts. The places where the y is 0. Okay, what else do we have going on? Next topic. Back to intervals, though, sorry. Next topic, back to intervals. Let's pause for 1 second, because we have still about 10 minutes left of class, but I want to go peek at our calendar really fast so we're all on the same page. Because with our calendar, we have Spirit Day on Friday, right?
Yes.
What are we supposed to be doing today?
I don't know.
Ooh, wait, I'm in honors. I am so sorry. No, I'm in regular? Ooh, let's try again. Oh, I think I updated yours with honors. I apologize. That's rough. We're finishing section 1.5 today, and that homework is going to be due tomorrow if we can get it done. And the reason why it's important to get it done is because remember how I said we were stopping halfway through chapter 1 to take a quiz?
What?
Yes. Because chapter 1 has 10 sections, and if we had a test on 10 sections, honors is doing it, but you guys, it'd be a little rough. Not that you couldn't do it, just in Precalc, I usually split things up a little bit better than that.
I think we need an extra review day tomorrow.
Oh, that's what I'm planning. I'm planning on a review day tomorrow. For us just to go over section 1.1 to 1.5.
No, just for it.
So we can have our quest on Thursday. Because Nathaniel, if we have an extra day, you know what the struggle is going to be?
We don't have any points.
No, you will. But it'll be after a 3.5-day weekend. And you know how high kids tend to score on quizzes and tests right after a 3.5-day
Which is
weekend?
why you should push it back even farther.
Yeah,
than Tuesday.
yeah.
Oh, that's a good
We
idea.
should
We
push
should
it back to
set
next
some
Friday.
time. We'll see. We'll see. I don't like to set you guys up for failure, so let's see how notes go. We have about 10 minutes left, and the goal is to finish 1.5.
Do we have a lot left?
So that you can have a nice 3.5-day weekend without any homework and a quiz under your belt, as opposed to stressing about or ignoring your first quest the day you get back from your 3.5-day weekend. Now, I told you guys this is going to have interval notation, yeah? Yeah, some of you are like, oh, that calendar, I should probably look at it from time to time. But I said we're going back to interval notation because we're answering a couple of questions, increasing or decreasing. Now, it shouldn't be that big of a deal, except numbers increase and numbers decrease, like x's could increase and x's could decrease. But what I'm talking about with increasing or decreasing on a graph, I'm talking about function values. So if I'm talking about function values, I'm specifically talking about y values, aka I'm talking about heights. So what's rising, what's falling, what's increasing, what's decreasing are the heights. Which is why we're literally just looking and saying, okay, when's the graph falling? Like literally falling, the y is decreasing. When's the graph rising? The y is increasing. Or staying constant.
Do you do it from
So
left
we-
to right?
Huh?
Do you do it from left to right?
Just like you would read a book, just like you would read English. So what you guys have over here are 3 graphs. Now, you don't necessarily need to worry about what's in blue, what the actual functions are, what the actual equations are. Instead, we're just going to answer for each one. Basic sketches are all that you guys need. Where it's decreasing, where it's increasing, and where it's constant. I'm throwing the constant in there because, well, this guy levels off. But when we answer this, when we explain where it's increasing, where it's decreasing, we are going to use x intervals. Because x intervals tell me how left, how right, how left, how right. They're going to show like the markers of each of these different locations or each of these different sections of the graph. Now the first one's easy. Because the first one, if you guys look at him, what is he doing the whole time?
Right.
Yeah. If you read him properly, he's just going up. Now, sometimes slow, sometimes fast, but he's increasing the whole time. So I can say decreasing, we can just say none. Constant, we can just say none. But for increasing, can't we say the interval negative infinity to infinity?
Yes.
Forever. From forever left to forever right, this thing's going up. But this middle one, still no constant, because there's no leveling off. There's no going flat. But yeah, it increases for how many pieces of this graph?
2.
2. It rises to begin with, and it rises to end with. There's only one decreasing section. You guys might not be able to see it. It's between -1 and 1 is where it decreases. How far left is the -1. And how far right, I forgot my comma, is the +1. Now here's where it starts to get confusing. I'm not talking about a point. So if it helps, you could put little x as an element of. You could put a little x as an element of. But it's understood to be an x interval when you answer this question. How left for this falling is -1. How right for this falling is 1. And so the rest of the intervals would be the rising portion. 2 different intervals, from -infinity up to 1. And then you could use a cool little union symbol if you want to be super like snazzy and mathematical. From 1 to infinity. So this whole portion from negative forever up to negative 1, it was rising. And then starting at 1 and going to infinity, it's rising again. Now we're getting these down as examples because the intervals start to look funny and start to look like points, but they're not. This last one, finally we have a constant portion. It goes flat between 0 and 2. It goes flat between 0 and 2. You need to put that little X as an element of to remind yourself that's okay.
Negative infinity.
It's rising, yeah, from negative forever up until that 0.
And then the decrease would be 2 to infinity.
And then at 2 it starts decreasing. Now some of you might be like, wait a minute, why aren't there brackets? Like there are filled in holes. What's the dealio? We just keep everything open when talking about increasing, decreasing, because at the markers, a change is happening, so we don't really say what's happening at the point. We ignore the middle location, just say what's happening before and after. So for intervals, I'm going to say use X intervals that are always open. Always keep them open. The book might say something differently. I disagree. And I'm getting you ready for calculus. Just trust me. Just trust me. But interval notation to answer the question, increasing or decreasing. Answer the question, increasing or decreasing. So take your time. The idea is easy. Oh, it's going up. Oh, it's going down. Oh, it's staying flat. Like the idea is easy. Just answering it with intervals gets a little tricky. Now over here, kiddos, there's a really complicated picture. And I'm going to take that really complicated picture away because it kind of just makes things a little bit harder than it has to be. The long story short for average rate of change. I know this section seems a little bit random. These are our last two ideas. Average rate of change. It's just talking about slope, and slope is so basic. Slope is just y2 minus y1 all over x2 minus x1. But what's different, kiddos, is that now you have function notation. It might just look a little bit more complicated, which is why we give you this formula. It's just slope, which we've already talked about. But the problem is they might do something like in the example over here where they don't tell you the y's because they're like, well, you know how to find y's yourself. Why don't we tell them to you? So the given information will just look a little bit differently because they're going to give you a function where you can get your y's from, and then they're going to give you some x values. So instead of giving you this crazy graph and having you draw a secant line and all this crazy stuff, instead, yeah, there might be a graph. But I want you to know how to do the algebra. If they give you x's, no big deal. You can plug in your x's. x2 minus x1 would be negative 1 minus negative 2 if I was solving this first example. But what I want you to see is that if they don't give you the y's, you can find them yourself by plugging in basically to the formula, but long story short is you're just getting the y's by plugging into the function to solve. So it's going to look different. That's kind of the name of the game for all of section 1.5. Some of the stuff is going to look different, but it's really what you've been doing all along, like with the slope formula. So you have to actually come up to the function and plug in negative 1 to the x spot.
Will it ever not show us the graph?
Yeah, which is why I'm showing you the plugging in. Because if it's the graph, could you just find the values that go with it and be like, sweet, I got it. But if they don't show you the graph, you still can totally do it yourself with the function by plugging in negative 1. But you would end up with a positive 2. Plugging in negative 2, but you would end up with a negative 2. So if you have the graph, yeah, it's awesome. Go find your y values. Plug it in, plug it in. But if you don't have the graph, you are not destitute of options. The slope is the same thing as the average rate.
How do you know what numbers to plug in? Does it always independently?
Well, it's all about what they tell you.
Oh, okay.
So they gave me x's, I went and found their y's, but plugging in would have gotten me the exact
So
same
you
y's.
just, okay, I got you.
You can do them from the graph, it's awesome. Go find the y's. can get them from the graph. You can also get them from the function. I'm just showing you both of them are fine. Okay. The last page is something that we've seen before. I just want you guys to notice when you see even in homework, it means y-axis symmetry, which you might need to go back to where we first talked about symmetry with our test points. And when we talk about odd, it's going to be origin symmetry. You guys can take a quick picture of this page because homework is going to be due tomorrow, but there are going to be new words. We've done examples of everything but even and odd. I'm going to show you tomorrow how the function of these things works, so you guys can use test points in homework. But I won't be super frustrated or mark you down if you don't do the even odd ones. Perfect. Right. Sound good? Good job, though. You guys rocked it for us to be able to finish up section 1.5. Questions tomorrow? Review tomorrow. Remember, 3.5 days, no pre-calc homework. It's a good goal. Hang in there.